Okay, can you see my screen?
Yeah, we can see it in Kirkland.
Okay, okay. So I will start it now. Okay, so today we will briefly cover the language model. From the word2vec to BERT. So it's just an overview, so that because it's too much stuff, so I will skip something and to put more attention on some important stuff. So here's today's agenda. So first we will introduce the background and also which content is not covering. And we will introduce word2vec, transfer learning, encoder-decoder, BERT, this important stuff. So let's start from the background. So when we think about the language model, the purpose of the language model is pretty intuitive. It's turn the text words or this textual data to some vector to make it a mathematical representation. Like the easiest one, it's like the one hot, like we can do just one hot encoding. So this is kind of it's pretty straightforward. So so when we think about the NLP tasks, like for example, like from sequence to sequence, which is actually it's encoder-decoder and plus task-specific model. So it's all using such kind of structure, like we will pre-process the data, and we will use some encoding or embedding mechanism to import this data to the encoder. This encoder can be any kind of stuff like word2vec, position, embedding, one hot, or CNRN, or some others. So after we turn it into some mathematical representation, we will use it in the downstream task-specific model, like classification model or some generation model. So so the basic idea, like for the first step, data, we don't need to mention, we didn't need to talk about it so much, because it's just it's some trivial stuff. But for encoder and task-specific model, so we always want this encoder to be as much easier as possible. So we want it to be such kind of general stuff, like the idea is borrowed from computer vision, which is the ImageNet in 2012. So it's providing pretty good model for computer vision in classification task. So for NLP, we want to do the same thing. So next, I will cover this language model or word embedding methods. So what will be not covered is I won't talk about this one hot backward word TFI. This kind of I will say it's kind of traditional methods. So from this long list of not covering, we can see we already for NLP this area we have such a pain. I would say it's such a pain in this path. So before 2030, the word2vec is given birth. It's kind of so painful to model the language. So so what is a language model? We will ask, right? So it's pretty, from mathematic perspective, it's pretty straightforward. Like this sentence, we want to, this C is kind of encoding, and we want to model this probability or some statistical relationship around the whole sentences. Since the language is generated, so we want to model this relationship, but it's hard apparently. So we turn it into some base conditional stuff, like these two guys. These two guys, like this one is based on Markov assumption that the current word is just related with the previous one word, and finally we can get this, like C is term frequencies, or we can say it's word frequency or any kind of frequency divided by this word's frequency, so that we can get some basic model. But we can see it's kind of hard, because to calculate this frequency, this term frequency, it's kind of hard, because when we have millions or billions of words to calculate, it's pretty hard to generate this stuff. And we are kind of harder to use this model to find the similarity, right? So it's almost impossible. Okay. So so following this, following this hard task, hard model, we have this neural network language model. So in this paper, which is a neural probabilistic language model, the biggest finding for this paper is it's kind of simple, right? It's just one layer, and which is it has an input layer, and it has some hidden layer, it has an output layer. It's pretty simple, but it turns out we can use this input layer. We can use this input as a word's representation. So it means after training, this input, it turns out it has some distributed information that we can utilize. So, from this paper, it found some kind of similarity between the word, like when it use this input representation to calculate the similarity, to calculate the score. It did find some relationship, but it's still pretty, I would say it's easy. So and the problem for this model is just using left n-1 words. It will not utilize the right words, which is following words, and it will cause a huge computation on output layer because it's fully connected, and it's hard to model long-range dependencies because it doesn't even have the relationship between words. So after this neural network language model, after a few years, so word2vec came to the world. So the basic word2vec is kind of method. These two papers propose this method, which is like the first paper, it proposed CBOW, which is continuous bag of words, and skip gram. And it also proposed some hierarchy softmax and negative sampling. These two guys are the optimization for training. Like the neural network, like the previous slide, method on the neural network language method, it will have a big problem on training because it doesn't have such structure to optimize the training process. So this hierarchy softmax, it turns the whole bunch of words, the whole bunch of vocabulary into the binary Hoffman tree, so that it turns the whole model, it turns the training process to the binary classification task, so that it will be much easier to train. And not to mention that in engineering perspective, it has a simplification of modeling and optimization on training, on also the tuning, the dynamic learning rate. So given that the last time we have talked about fast text, it's pretty similar. So I won't go to the details of word2vec. So this is a structure of the CBOW. So we can see that CBOW is kind of simple. So it's using the context words, which is like if we set the window to 5, we will use the previous two words and the two words afterwards. From so that these 4 words, we average their representation, and we use this average to represent the current words. So and in the practical training, it turns this metric into that hierarchy softmax, so that it will maximize this formula, which is we can see that the CT is context, WT is current word. We want to maximize this log probability, so that we can, in this process, we can get, we will train this matrix. We will train this matrix. Basically, we won't train this matrix. It's just the average. We will just train this matrix, which is actually the hierarchy softmax, and we get the word2vec model. So skip-gram is it's simple. It won't use the average. It's using one word to predict the words in the context window. Like we will use this central word to predict previous 2 words and the next 2 words. So and of course still using the hierarchy softmax. So finally, it generates this graphy. It's kind of a classical graphy. So it can find the similarity and distance between words. So after word2vec, we will introduce GloVe. So for GloVe, it's the idea is pretty straightforward. So GloVe is using the concurrency frequencies. Like in here, Xij is a concurrency frequencies, and here, right? So this formula, which is the loss function, we want to minimize this loss function. So ignore this Bi, Bj because they are bars. And so it turns out we want to minimize this Wi product with the Wj minus log Xij. So the idea is to make this product as close as the log of the concurrency frequencies. So yes, it will be pretty straightforward if I use this. So it will do a log. First, it will calculate the co-occurrency matrix, and it will do a log to make it as close as possible to this product. So this product, this guy times this product, this guy times this guy, it will be close to this guy, so that we can use this as the word embedding. Okay, so next I will talk about fast text. So the difference between it and word2vec and GloVe is it can utilize labeled data, which is supervised training on classified data. So it's like the structure is the network structure is pretty similar to CBOW actually, but instead of predicting a word in CBOW, fast text is predicting the category. So we can say that it's kind of supervised task. And another improvement is instead of using bag of words, it's using bag of features, which is the mixture of words, bigram, trigram, or even 6-gram. So from practice, it's using words, bigram, and trigram together to do the average for these 3 embeddings. Okay, so so far we talk about the method, which is started from the word2vec. So it gives us a method to do the distributed representation. Like this idea of distributed representation is, I would say, is kind of a genius idea, because it's distributing the information of one word to the other words, so that when they appear together, we will have the information about these 2 words or multiple words together. So, and it introduced the pre-training embeddings idea. It's like after you train a word2vec or fast text, you can utilize this word embedding directly in your task. You don't need to figure out a way to represent your text data. So it turns out currently everyone who is doing NLP, I would say almost everyone is utilizing this idea. The 2 reasons I can figure out that you're not using it. One is you're so rich, so you don't need to hire like thousands of labels to label the data. The second is you're acting like recklessly, and you are probably in a wrong direction. So next, following the word2vec, I'll talk about the transfer learning, which is utilizing the pre-trained embedding. Okay, so the first one is PV DM or PV DBOW. So this guy, PV stands for paragraph vector, which is what we are using. So the idea is much simpler. So this structure is a CBOW structure. And we just add an additional pointer, which is a paragraph ID, to this structure, so that when we train the word2vec, we will also get the representation of this paragraph. So I will call this paragraph vector as some side effect of word2vec. And this structure is skip-gram. So instead of to predict the word together, we will have the paragraph matrix, which is pointing to every paragraph, so that after the training, we will get the paragraph vector for each paragraph. So for this paragraph vector, it's kind of for each, if we just want to model a paragraph, it's fine. But it's kind of, it's harder to model semantic information between words, because it's just pay attention to one paragraph. It won't have such more semantic information. So
they're average slash
what? So average. Yes, you will do the average for the paragraph vector and all the words together. Do the concat, yes, we can, yes. So concat, there is some practical example that we can utilize in the classification task. That is to add another ID or which is a class label. So that together with this, together with the training of this network, we will have the embedding for that category, for that class label. So next is skip sorts and quick sorts. So we know that skipgram is based on words, is trying to predict words. Instead of predicting words, skip sorts is based on sentences, meaning it's trying to predict sentences based on the context sentences. So to model sentences inside one sentence, it will use RNN sequence, and between sentences, it will also use RNN sequence. So it's I will say it's kind of a draft of encoder-decoder because it introduces the idea of encoder-decoder utilizing RNN sequence. See, it's kind of it's pretty straightforward. So we will use RNN sequence to encode the bunch of meaning of a sentence, and we will use the output of the encoder, and we will utilize the output to input it to the decoder, so that the decoder will output some the sentence embedding. That sentence embedding will represent the information we want. So so instead of the generation task in skip sorts, the quick sorts turns the generation task to classification task. So this idea we will target about it many times, because for this natural language task, the generation task is usually it's much harder than classification task. Even in the current modern language model like BERT, it will turn the generation task to classification task to get better performance. So quick sorts also utilize the positive sampling and negative sampling, which is the idea borrowed from the word2vec. Like if it will randomly sampling some sentence. If this sentence it is inside the context of the current sentence, it will call it positive sampling, and it will benefit the function. And outside is negative sampling, which is it will generate the loss. Okay, so this idea is also borrowed by BERT. Okay, so let's go to the next. So next I will quick go through the encoder-decoder model. Actually, not encoder-decoder model. It's about the structure that utilize encoder-decoder inside their structure. So like this info sentence introduced by Facebook is using bi-RSTM. It's trying to use bidirectional RSTM together with some stability introduced by the residual network, together with the max pooling as the encoder. And also following the info sentence, we have the general purpose sentence representation. It's using it's combine 4 supervised tasks to learn the sentence representation. It will use these 4 specific tasks to train their embedding model, to train their language model, and it turns out training on these 4 tasks gives better performance on each single task. And this universal sentence encoder is utilizing transformer and DAN as encoder. We will talk about in transformer in detail. So there are so this multiple task learning. We can see it's for this general purpose sentence representation. So generally, they are using multitask, or they are using different encoder to try to get a better language model, to try to represent as much or as more as information as possible of the information inside of the language model. So after they get the language model, they will do the transfer learning on different tasks, and they will do the fine tuning. As they will use some simple layer followed by the pre-training network to do the different tasks like classification task. So until now, it's still straightforward. But so what's the next? We will think, right? So how can we utilize, how can we borrow the encoder or decoder trained on these tasks? How can we utilize them generally? Like for this task, for this structure, they are still using some specific tasks. They are hard to make it general. So so here the down is coming. So the idea is, in the machine translation task, we will train the encoder and decoder. So we will get these guys. We will get encoder, decoder, and for some task-specific model, for some specific tasks, we will directly use the encoder borrowed from the trained model, and we will utilize them in the downstream tasks. So let's go to some details. And by the way, this structure is called contextualized word vectors. So the name is telling us this encoder can encode the context into the word vector. So it's using word vectors as the input of the encoder and train on these word vectors, and this encoder will encode the context information into the language model. So because this guy is still supervised, so we want to make it unsupervised, because in the real world we really don't have so much level data. So here comes embeddings from language models, which is ELMO. The paper is in deep contextualized word representation. The idea behind it is to utilize two-stacked bi-area STM and residual network. The residual network is to making it more stable, because the residual has a functionality that can drop some parameters so that the model will be not so much sensitive to the learning rate. So, and the function we are trying to maximize is straightforward. this guy, we want to maximize it because it's utilizing the previous context, and this guy is using the next context. Okay, so another paper, which is a universal language model fine-tuning for text classification, the important features it introduced is the fine-tuning methods. So first step, it will train the language model on the wiki text, which is around 100 million words. And for some specific data set, if we want to train a ServiceNow language model, we will utilize the data we have in ServiceNow, and we will fine-tune the language model we trained on this wiki text based on data, the ServiceNow data. And we get the so-called second fine-tuned language model. And for the next task, like if we want to do the classification, we will utilize the second language model and plus a simple classification layer to do the classification. So the other important feature it introduced is fine-tuning tricks, which is utilizing frequently. So the first is the discriminative fine-tuning. So this guy basically it's to use a different learning rate on different layer of the network, because we know that like in computer vision, different CNN layer will capture different scale of information of this picture. So same thing for the natural language, different layer will also capture different information. Like it has been proved that for the word vector, for the not with the word vector, for the first layers, it's trying to capture the semantic information and the stop words, and for the deeper layers, it's trying to capture the word information. So for different layers, we kind of want to use a different learning rate for different layers. The second trick is slating triangular learning rates. So it's like after because we are fine-tuning the language model based on the pre-training network. So when in the beginning of the training, we want to use some lower learning rate so that the pre-training network won't change a lot. It will keep stable so that the next training, the next epoch will capture this information from the pre-training network. And after the beginning, we will increase the learning rate to accelerate the learning. And after the middle of the epochs, after the middle of the learning, we will decrease the learning rate so that we will make this training converge. So the third one is so-called gradual unfreezing. It's used in this third fine-tuning, the third step. So because when we just add a simple layer like a classification layer, we don't want the language model change it a lot. So we want to kind of fix the language model. So when we train the classification layer, we will unfreeze the layers which is closer to this classification layer. And gradually, we will unfreeze the remote layers, which is far from the classification layer, so that this information will be captured as more as possible with this gradual unfreezing. So these tricks, these fine-tuning tricks, is utilized frequently in this pre-training network world. So okay, so the previous introductions, they are all about the base before BERT. So before BERT, I want to introduce this important structure, which is a transformer structure, and we also can call it as a sequence to SIG, or encoder-decoder. So the mechanism here is all based on this self-attention. So you may ask, what is self-attention? So why it's called self-attention? Because it's kind of it's trying to pay attention to itself. So this guy and this guy, this and this guy, Q, K, V, these three metrics, they are all the weights based on, or we can call it, they are all the weights calculated based on the word embedding of the original word. So let's go back to here. So let's go through this process. So let's say we have two words, and we embedded these two words. Like let's say we use fast text, and next we will first to do a dot product with use this X and W, and this W is multi-head. It's based on, let's go to here. We see there is a parameter which is DK, right? So this DK is controlling the scale of the attention. So here we have three heads, which means we will have three scales of the attention. So after the multiplication of X and W, we get a new matrix. And we will use this new matrix. We will do the multiplication between this W, this output of multiplication of X and W, to this guy, which is QKV, and the calculation function is here. So and after all this stuff, after W, Q, K, V, we get Z0, and this Z0, after we get this Z, we will do a linear projection with the WO. Don't be confused with this W and this W. They are totally different. They are different things. This W is just simply a matrix. After it, we get this Z, which is output of this self-attention layer. So we can see that this Z and this X, the output and the input, they are the same dimensions. So, so you may ask why it works, right? So my explanation is, like this K and this Q, they are just simply the matrix, but they capture the information of the context. So we can think this whole bunch of soft max is just a width, and this width is applied on this V, and this V, so that so that this whole softmax will have the information captured from the semantic perspective. And this way, let's think it as a translation task. This way can be the different language. Like if I want to translate English to Chinese, this way can be the previous Chinese words. And this Q and K, they are the information captured from English, the semantic information of the English. So this width times we do a multiplication of this width, and we will translate these previous Chinese words together with the semantic information from English to a new sentence, to a new words, which is Z. Okay, so we can have deeply details in the next slides. So this structure of encoder and decoder. So it stacks much layers of self-attention. So apart from self-attention, it will do the add and normalize. It will do the feed forward, and finally it will do the add and normalize. These three layers, they are basically to make this self-attention, to project the output of self-attention to a linear space. Okay, so and between each this whole bunch of layers, it will have that residual layer to improve the stability. So, and which is decoder? So this is a decoder. So we can see that there is not too much difference between the decoder and encoder. The only difference is in here we can sync the whole encoder and decoder as a self-attention. So here, like this line, it is the Q we mention. No, the K we mention it here, and this input, this guy, it is the way we mention it here. So the encoder basically, together with the encoder, they are a huge self-attention. Okay, let's go to the next. So this slide is an example of the translation we just mentioned. Like I don't know what is the language, maybe French. Okay, let's say it's French. So we want to translate French into English. So this encoder will encode the information from the French, and this information is utilized in this decoder, which is KV, and this guy we can think it as V in the self-attention formula, so that together they constructed as a big self-attention. So the output will be the prediction of the next word. Okay, so next, before this whole positional embedding, I will talk it in BERT. Yeah. So before BERT, there is a pretty important work, which is generative retraining. We will talk the idea later, and the few features BERT has is a real bidirectional transformer. So I will explain why we call it as real. It doesn't does it mean any other previous works, they are all fake bidirectional transform. So, and the second is a mask LM, which is a mask language model. And third is next sentence prediction borrowed, the idea is borrowed from skip source. And fourth is a universal structure introduced from GPT and improved in BERT. So let's talk about the so-called real bidirectional transformer. So previously, when we are talking about the self-attention, we know that it's stacking the self-attention layers, and in BERT, it's stacking 16 self-attention layers, and in each self-attention, it will have 16 hands, which means it will have 60 skills in here, so that we can think it as like it will capture the information from 16 skills. So given that it has 16 layers, so we call it deep networks. So this graphic shows the information integrated between different words. Like the more deeper the color, the more information the word has. Like for example, the word love. The information of love is represented in the embeddings of the love, be perfect, and the other words. So it means this 16 hands self-attention and this 16 layers of network, it's integrating the whole bunch of information of the words. It's distributing the information of one word to almost each other words, so that we cannot. So it's like we cannot use it. We cannot use it as some single embedding, like a word2vec. Like word2vec, we can just for each word we will have some unique. We will have the unique word embedding. But here, the BERT, this self-attention, it distributing each information to each words, so that together, these words together, they will have the semantic information. They will capture this semantic information. So one of the problem for this bidirectional is it's kind of leaking the information you want to predict. Like if we want to predict if this sentence is, we are importing this sentence to the network and to train it, and in the middle of the training, we want to predict like perfect, right? But this bidirectional, it's already given the information of the perfect, right? It's kind of leaking information to the training. So how to avoid this this leaking? How to avoid this disadvantage? Here it comes the mask language model. The idea is very simple. So let's say we want to predict W4, which is the word, okay? And we use this mask to mask it. So that when we do the prediction, when we do the training, even if the bidirection bidirectional self-attention, the transformer cannot have the information from this mask. So to recover it, the current word that we are trying to predict, we will mask it, and we will do a classification based on the whole bunch of vocabulary to predict which is the word is masked by this specific mark. Okay, so here we can see that it borrowed the idea of turning the generation task to classification task. So this classification task will be on the size of the categories will be the size of vocabulary. So it's the classification of the whole vocabulary. And the third feature is the next sentence's prediction, as we described it in skip thoughts. So the idea is, given two sentences, we will predict whether they are neighborhoods. So like we will do some random sampling. Like for 15%, we will give the next sentence, which is they are the real neighborhoods. And for another 15 probability, we will randomly give it. So it's kind of negative sampling borrowed from word2vec. So this idea still, it turns the generation task to binary classification task, which makes this task with all the training much easier. Okay. Next, let's see the loss function of the BERT network. So I will say this loss function is kind of useless because it cannot in practice we cannot use it to guide the design of the network, but it's still straightforward. The L1 part, let's take a look on the theta 1. This theta 1 is a parameter from here, from the classification layer of the masked language model. And this theta 2 is the classification for the next sentence's prediction. This theta is the parameter of the network. So pretty straightforward. We add them together, and we are trying to minimize this loss function. Okay, so after loss function, I'd like to talk about the training tricks in the BERT. So as a learning rate warm-up, which is a universal language model we have described before, that 3 tricks for the learning rate. And instead of ReLU, it's using GLU, which is a new activation function, and not trivial. It's using dropout to make it much stable, and other thing I need to mention that it's utilizing 800 million from this dataset and 2,500 million of Wikipedia dataset, and together it has around 3.3 billion words to train this BERT. So it's also providing a pretty good framework for the fine tune, which is that we can use. It will be much easier for us to use it in the 4 specific tasks. So, for example, to do the input embedding, like it will plus the position embeddings, where the positional embeddings, it means it will capture your positional information. Like it's pretty straightforward. Like here, it's from E0, E1, E2, E3, etc. It means for each embedding, we can think it as some kind of index that can capture the position information of the words. And it also do the segment embeddings, where we will have a segment model to get the segment embeddings. It means to capture segment information. Like here, we have just all in EA and EB. And finally, we will have the token embeddings, like word2vec. For each word, we will have different word embedding, and we plus them together. We do the average, and it constructs the input to our pre-training BERT network. So these are 4 specific tasks that paper mentioned. Let's take a look on this classification tasks. So after, okay, it's a final slide. Okay, so after the input embedding, it's we get all the input embedding and we import it to BERT, and we get the output together with the class lab. And this class lab is based on the classification layer we placed after the BERT. And for this single sentence classification task, for this question answering task, single sentence tagging tasks, this paper does provide a very universal framework to do the fine tune. Okay, so let's do a summary of BERT. So first, it's utilizing transformer. It borrowed the idea from transformer, and for that negative sampling, it borrows the idea from CBOW. And for the next sentence prediction, it borrowed the idea from skipgram. And for the framework, for the universal fine-tuning framework, it borrowed from GPT. So yeah, that's a reason why I didn't provide the related materials in our spreadsheet, because if you really want to know the related materials, you really need to read a lot of papers before BERT. Okay, so I just quickly went through all the do an overview for the language model. So any questions and or any discussion you want to discuss?
It was a long session.
It was, yeah, it's pretty,
Yes, it is
a lot of stuff.
So the positional encoding is talking about some divisional extension. So it's this business of having multiple findings by sign and cosine functions.
True.
Which is sort of how they get away from having any functions.
Yes, that positional embedding is introduced in that sequence-to-sequence paper, and it reduced that not reduced. It's kind of embedding. The problem for this transformer, right? It's not like the regular process. Like we import the words one by one, right? So that's embedding. It will capture that position information, right? So it's not like what we are doing for some Euro task. Yeah.
So in BERT, what did they introduce? Did they introduce the indexing of the whole sentence? What did we get out of the BERT when we used the BERT system? What is the difference of the previously BERT embedding, globe or other things? So what is the major difference?
Okay.
That anyone could remember when someone talks about BERT?
So BERT is, I will say the most important feature is it gives a very good transfer learning idea. So like for the word2vec, right? We train our word2vec on a big data set.
Right.
And for each word, we get this kind of a word vector. But that just, they are kind of just this word information, right? To use it, you may need a lot of things to capture the information. Like we want to do NER, right? We want to tag the word, right? So that we can utilize that tagged information together with the word2vec information and do the next task, right? Mm-hmm. But this BERT, it gives us that, okay, you can utilize this network directly. On above this network, above the BERT, you just do a very simple, just a one-layer classification layer, and it will do the classification task.
Whether the sentence comes after or before the sentence or not, that's the classification algorithm, right? That binary classification. Whether this sentence.
No, our task. Like now we want to do the classification based on ServiceNow dataset. We have that categories, right? We want to build a classification model, right? So now we are using TF-IDF or word2vec. And it turns out we need to do a lot of jobs to make the word2vec better, to improve it. But in here, for this BERT, you can build a classification layer above the BERT network, and it will just and you can just import your data into the network. That classification layer will simply give you the output of the category, right? So basically, it's kind of
easier to train.
It transfer the information you trained from the previous data from the pre-trained. They are another data set, and you can also like I mentioned before, you can also use all the ServiceNow data set to fine-tune the model. And after 2 steps of fine-tuning, and you do the classification, this model can capture the semantic information, can capture the specific information.
So do you have any idea the size of the model? Because the data set they use is a huge data set.
Yeah, it's.
So if we ever want to do this kind of a thing, right? And what is the size that we are talking about? Because then they must have captured a lot of different meanings of different combination of the words, including the group word, sentence, and everything. So I'm assuming this is going to be a big model.
True. It's around gigabytes. Yeah, the model
so this
is
similar to what syntax net model that Google is right now releasing, right?
Yeah. Yeah.
So is it even like multiple size of syntax net model, or is it around? So it's like
Multiple size.
Multiple.
It's huge.
Okay,
It's deep model.
Yeah. So once we put this model in one of the prediction servers, it has to be shipped inside as part of the prediction server.
Yes.
That is the idea.
Yes.
And when we do the training for our classification task, we will kind of send this data over to the prediction server or trainer server. Or so, do you have an idea how long the training also takes? You say it's just simple layer, right? So yeah, but the timing wise, let's say if someone wants to train with the BERT, is there any numbers out there?
Yes. Inside the paper. Yeah. We can go straight to this paper. It's yeah, at the end of oh shit, not in this paper. Damn. Okay. Not in here. Shit. Let me find in my. Okay, we have. I have some. Oh, come on.
So you can look at the later.
Yeah, it's coming. It's coming. Yeah, it's coming.
I'm going to model I'm very shiny.
Here, yeah. So the training time of GPT is 1 month. For BERT is 4 days.
1 month versus 4 days. Oh.
Yeah. So yeah, GB. Yeah, with 64 GBs. Yes.
CPU.
Yeah, of course.
GPU.
So TPU.
So how many layers?
For what?
BERT?
For 16.
16.
Yeah.
Oh.
The data set input is quite different for the BERT.
Yeah, the parameter for BERT is 340 million.
Yeah, it's a lot. This is already trained for us, right?
Yes, it's already trained.
The size is nothing. This is not gigabytes. So if you say
Is that
No, it is.
Is that the size of the trained network?
True.
The size of the BERT is 340 megabytes now.
No, not megabytes. The parameter.
Oh no, sorry.
The parameter is 340 million parameters.
Okay.
So.
The main motivation is to have some kind of provide a classification framework using the embedding. Embedding. So
Yeah.
that's the main motivation behind it.
Yeah. To universal network.
Universal.
Yeah.
So other problems can be solved.
Yeah.
It's impressive.
There's this chatbot called Hugging Face.
Oh, Hugging Face. Yeah.
Terrible name. They are real focused on met some of the guys at these conferences. They're very proud of the fact that they can chat about Justin Bieber with teenagers in China. I think it's completely the wrong awful discourse for us, but they're doing a good job at adapting. They did a PyTorch implementation for, and they said they didn't even attempt to retrain it. They just used Google's weights.
Yeah.
And how they are gonna
That's what it takes to memorize all of English literature.